So we would like to compute the double integral of the function x plus 3y over d, where d is a parallelogram given by the four lines that are listed here. And we wish to do this by performing a change of variable. And let's once more recall how such a change of variable is performed. So suppose that you have an integral. Again, I've been denoting the differential. Instead of writing it as dA, I'm denoting it by dx dy in order to emphasize the use of the variables x and y. And pretty much we have to rewrite this as an integral over d prime, where d prime is the description of actually I should say the set d expressed in the new variables u and v. And the integrand is replaced by the function where x and y are expressed in terms of u and v, and we multiply by the absolute value of the Jacobian determinant. And here, let's emphasize again that we have an integral with respect to u and v, so this is really our dA right here, and we should say that the Jacobian determinant is the determinant of the first partial derivative. So on the first row, we put the partial derivatives of x with respect to u and v. On the second row, we put the partial derivatives of y with respect to u and v. Okay, so this is the formula that we should work with. And in our case, let's try to see how all these things are done. So basically, the idea is that we have to take the lines that define our parallelogram. By the way, let's try to sketch it so that we get a rough idea of what it looks like. So something like this, it consists of two horizontal lines and then two lines like so. My proportions are not so correct, but this is roughly what we expect this t to be look like. And obviously the problem with computing such an integral, it's not such a huge problem since the integrand is so simple, but you would have to break it into three separate integrals. By performing this change of variable, we will try to get a new domain, which is a nice rectangle with sides parallel to the axis. And that's pretty much the main idea. So, so how do we do this? We will try to see how the bounding lines are transforming into u and v coordinates. That will give us the new bounding lines for the domain in terms of u and v. So, for example, if I take the x plus y equals 10 line, and now I replace x by u minus v and y by v, which is how x and y are expressed in terms of u and v, then I simply get u equals 10. And similarly, if I take the x plus y equals 6, that will give me u minus v plus v equals 6. So that will give u is equal to 6. And if I take y equals 3, then that will give me v equals 3 and y equals 1 will give me v equals 1. So here are the new boundary lines. So obviously what we're dealing with is a very nice rectangle. So let's say u equals 6 is here, u equals 10 is here, v equals 1 is somewhere here, v equals 3 is somewhere here. Again, my proportions are certainly off, but we get the picture that we have a very nice rectangle that looks like 610 cross 1, 3. Okay, how about the integrand? So the integrand is x plus 3y. So x plus 3y is going to become u minus v plus 3v, which is u plus 2v. So that's the new integral. And finally, the Jacobian. The Jacobian here is really simple because if we take the first order partial derivatives of x and y with respect to u and v, what do we find? For x, we get 1 and -1. For v, we get 0 and 1. This determinant is 1. It doesn't get any simpler than that. So our integral is going to look like what? So first of all, we're over a rectangle, so we put 6 to 10 du, and then 1 to 3 dv. We have our function, which is u plus 2v. And let's recall that this is multiplied by the Jacobian, which is 1. I'm putting this for formal purpose. Of course, nothing changes. So we can do u squared over 2 plus 2uv going from 6 to 10. And then we have 1 to 3 dv. And this is going to be 10 squared is 100 divided by 2. That will give us 50 plus 20v. And then we subtract from it what we get by plugging in 6. So this will give us 6 squared, which is 36 divided by 2. That's 18 minus 2 times 6 is going to give us 12v. And this will be for v from 1 to 3. So this will give us 32 plus 8v from 1 to 3 dv, which is going to give us, of course, 32 v plus 4v squared from 1 to 3. And that will give us 96 plus 36. And then let's subtract what we get if we plug in 1, which is 32 minus 4. And when everything simplifies, we get 96, which is our final answer for this integral. I mean, certainly, if you try to actually compute that in x and y coordinates, you will see that it's not an impossible computation, but this is much faster after we do this change of variable, which, by the way, was an extremely simple change of variable. And that's all. Thanks for watching.